Let's start this video asking a question. This is you throwing a ball. Now this ball is going to travel something like this. You're going to throw it up. It's going to go back down. It's a basketball. Okay, cool. It bounces off, whatever. We don't care about whatever happens once the ball touches the ground. But when you throw the ball, notice that it's going up, right? And it's moving in the x direction. So what does that essentially mean? That means this is a two-dimensional problem. Now, if we were to represent this, this is how it would look like. Cool. We have a y-axis and an x-axis. Cool. Just like that, your ball is moving in these two coordinates, right? This is how we represent an object's motion in two dimension. We consider the y component and the x component of a particular object moving in a direction. So this is a vector essentially. So what that means is a vector has components. It has the y component and the x component. Cool. But what exactly is range? Now range essentially concerns the movement across the x dimension. What that means essentially is that if you were to throw the ball something like this, it's not that high. It ends right over here. Let's mark that position, okay? Now your friend over here is an athlete. He's been training for the Olympics, and he can throw it a lot higher than you can. Cool. But guess what? It ends up in the same spot. So is the range the same? Guess what? You guys traveled the same distance. Your guy's ball, when you threw it, traveled the same distance, so you have the same range. Cool. Now let's quickly understand this through a mathematical approach. Now, don't get intimidated by this. Let's think about it logically, okay? We have a ball that's going in this direction, okay? That doesn't really mean that much to us because, we don't really understand what this means. And the way we understand it is by breaking it down into two components. As you guessed it, the y component and, let's keep this different colors so we can understand what's going on. The y component, right over here, whoops, excuse me, the y component and the x component. Cool. Now, how do we exactly represent this? Now, imagine you're reading a question that say that the angle is relative to the x-axis. Okay, cool. What does that mean? That means there's an angle over here that is relative to the x dimension. This is how you're going to represent it. And again, this changes for every question. You have to understand the question, and that's what really physics is, breaking and understanding what the question is saying, more than memorizing anything. So, okay, how do we mathematically represent this now? Now, I want you to appreciate the fact that this can be seen as a triangle as well. This is not a appropriate representation because normally, okay, let's just delete this part at the top so it's more understandable. So this right over here is our triangle. What that means is if we were to find, if this was a normal trig question, right, you would be like, okay, so katoa, cool. We're trying to figure out if we were to represent this over here, let's call this y. Let me just get the color. Let's call this y. Let's call this x. How are we supposed to mathematically represent this relative to theta? Okay, that's not a problem at all. If we were to represent the y-axis, right, we realize that this is opposite over hypotenuse. So SOHCAHTOA, right? Look at that. Sine of theta equals y. Whoops. Y divided by x, or excuse me, y divided by the vector itself. So why is this the vector? Because the vector is the hypotenuse over here. Now, if I were to ask you to represent this equation in terms of y, how would you do that? You would just multiply both sides with the hypotenuse, which is the vector. So this is what it would end up looking like, wouldn't it? Let me see. So y equals sine theta multiplied by the velocity itself. Cool. This is the component of the y. Now let's see the component of x. Now x over here is, let's see, is it opposite? No, it's not. Is it adjacent? Yes, it is. So we can say that cosine of theta multiplied by the hypotenuse, which is the velocity, multiplied by the velocity, equals x. So we have this established. We understand this is how you mathematically represent the two components of this vector. So how do we write range? What's the formula for range? Now let's think about this logically, okay? If you were to throw this ball and I were to ask you what is the final position of this ball, you would probably remember this equation: x final equals x initial plus velocity initial multiplied by time plus 1/2 acceleration times squared. But we can't really use this equation right off the bat because we have two components like we established. We have the x component and we have the y component. So what's exactly going to happen is, on a conceptual level, you're going to essentially write this equation in terms of the x component, and then we're going to use the y component. We're going to solve for t and plug it back for x. So that might be a lot to take in. That's totally fine. And that's why we're going to break this down and watch what I mean exactly. So yeah, let's write this equation first in terms of the x component. So the x component would be x final. So hang on, let me just write this. So x final equals x initial plus the velocity of, guess what? Which component are we talking about? We talk about the x component multiplied by time, and then 1/2 of acceleration times squared. But in these equations over here, acceleration is always constant. So what we can do is, because acceleration is 0, we can just ignore this for now. What happens next is we have to think about this logically. Okay, so the final position of x and the final position and the initial position of x, how do they relate to one another? Well, we know that the initial position of x is actually 0, so we don't care about that as well because we set it. We set it at the origin saying that it's 0, so we don't really care about that. We can say 0. So here's what's going to end up looking. Our equation is going to look like this: vi of x multiplied by time. Okay, but we have to represent time in... we had to represent time. We need something to represent time that is in relation to these coordinates, and that's where the y component comes in. So if we were to use the exact same formula on the y component, this is how it would look like: y final equals y initial plus the initial velocity on the of the y component multiplied by time minus 1/2 of gt squared. Now you might be asking, why is this minus? What is this g? And really what's happening over here is g is the acceleration of, basically due to gravity. So if you were to throw an apple down, just like Newton, an apple fell on his head, there was a gravitational force of negative 9.8. And often what happens is we're going to end up seeing this negative over here because we're bringing this negative and just putting it over there. So that's why we have a negative. So now let's think about this. The final height, where is this going to be? We threw the ball, it's going to be on the ground again. So like let's imagine this, right? You threw the ball, comes back down again. That's the final height. So that's 0, okay? Now what's the initial height of the ball? Well, you threw it from the ground as well. So that's going to be 0 as well. That's 0 as well. So what does this exactly mean? We have an equation that looks like this at the moment. Whoops, let me just break this down again. So the initial velocity of the y component multiplied by time, 1/2 gravitational force multiplied by time squared. Now, what we can do over here is factor out the t, because remember, we are trying to figure out how to represent time in this equation right over here. So what we're going to do over here is we're going to factor time out. So if we were to factor time, this is how it looks like, right? Time, the initial velocity of the y component minus 1/2 gt. Okay, that's what we have. Now, this equals 0. Now, imagine that you were trying to solve for time. We have two possibilities over here. We could divide this entire equation by time and this by time. That will cancel out, and we have this part of the equation equals 0. But what is the point? Why are we multiplying? The entire concept behind this is that if you multiply by anything by 0, it's going to end up being 0. And the other possibility we have is we could divide, or we could divide this entire part. So divide this whole part by this over here, whatever's inside this. And if that were to happen, we would have time equals 0. But that doesn't really mean anything. So what we essentially end up doing is we multiply both sides by time. So if we were to do that this time, divide both sides by time. Excuse me, I might have said multiply before as well. So this is how it ends up. This is how it looks like at the end. Y minus 1/2 of gt equals 0. Now we can simply solve for t. We can rearrange this equation and solve for t. Let me just put this down a little bit. Resize, put it down. So let's solve for t. Now t is going to equal negative 1/2 gt, because we just divided or subtracted each side with the initial velocity viy. So viy, we can cancel out these negative signs. We can multiply the other side by 2, that goes away. And then we can divide this by g, which is the gravitational force. So t equals 2 times the initial velocity, the y component, divided by g. Now, if we were to put this back into this equation right over here, what's going to happen? Well, let's figure it out. So I'm going to delete this part. Delete. So x final equals the initial velocity of the x component. And we know that the initial velocity of the x component, what is this going to be? Well, we have already represented this over here, this side over here. So it's going to be cosine theta multiplied by the velocity itself. And then we're going to plug this. So we're going to plug all of this t for this. So we're going to end up getting all this over here multiplied by this. So what is the initial velocity of the y component? So let's break that down as well. The initial velocity of the y component, as we see over here, is sine theta multiplied by that. So sine theta multiplied by this over here. And let's not forget that we have a 2 here as well. So there you go. Now, what happens essentially is we recognize this trig formula over here. What we see is we have cosine, let me just get this. We have cosine, 2 sine theta, cosine theta. This over here equals sine theta, sine 2 theta. So we can replace all of this for that. So what does our equation at the end look like, essentially? Well, let's see. The x final equals the initial velocity squared, or the velocity itself squared. Well, we call this initial velocity short. So the initial velocity squared, sine 2 theta, all over g. And let's make sure that this is not negative, so we're going to add these over here. So this is essentially the range. So xf can be written as the range itself. Now, you're going to utilize this range whenever you're asked to find the final position of the ball thrown off or whatever. You want to memorize this equation so you can just plug in the givens and you find your range. So that's what range essentially is. And one thing to be aware of is if you see a question, something like this question over here, where they're asking you to find the location of the ball once it bounces off a ball, a wall, you can't really use range anymore, because now this is basically a problem where you have 2 sets of different problems to solve. So you would essentially treat this equation or this part of the problem different to this part of the problem. So just remember that range only applies when there is nothing blocking off the x dimension. So, it's something that's easier to calculate. So we would calculate this an entire different way.